Hello and welcome to the second video about this rare 486 EISA/VLB board. As I said in the last part, I borrowed it from another user of the German DOS Reloaded retro community for some experiments. However, the board was dead and I had to repair some broken traces. There was also that small fiasco when I was trying to make a battery mode, but if you didn't see the first part, feel free to take a look. After some back and forward, the board was back to life and I promised to show a bit more of the EISA configuration and do also some benchmarks. So let's take a closer look. Before I show the configuration software, let's come back briefly to the history. This board is special because it has three types of slots for expansion cards: ISA, VLB and EISA. As I mentioned in the last part, EISA was introduced as a competitor to IBM's proprietary MCA bus, which was used in PS2 machines. EISA, which is properly pronounced EISA, if you believe Wikipedia, stands for Extended Industry Standard Architecture. It was developed by a big consortium of computer manufacturers named the Gang of Nine. It had nearly the same list of supported features as MCA. It supported up to 32-bit wide data transfer, bus mastering and configuration per software, which shall be the actual topic today. EISA or EISA was primarily developed for servers and workstations, so most expansion cards for it were network adapters, SCSI controllers and similar stuff. So basically hardware which handles a lot of I/O and would benefit from better bus control flow. EISA hardware was obviously more expensive than ISA, and so it was rarely used in private computers and office machines. This detail is important because as IBM developed its MCA bus in 1987, it introduced an interesting feature which made system administrators jealous. If you ever configured a good old 386 PC, you might remember all those jumpers for ports, interrupts and so on. Imagine you have a fleet of machines which you need to configure. Open the case of every one of those, set the jumpers accordingly, maybe keep track of other custom hardware which is installed in that machines and then try to reorder resources accordingly. Doing that for one machine is okay, but for many servers or workstations that could be a real pain. Later, many ISA expansion cards got own EEPROMs where settings could be set in software, but they all needed custom software which was very hardware specific. Though that was a step in the right direction and at least provided a way of hardware configuration per software. However, the real breakthrough in PC market was introduced by IBM with its MCA bus. As I mentioned, among other features, MCA provided a standardized and centralized setup utility which could be used to assign hardware resources and assign settings for the installed hardware. As EISA was developed 1 year later, this feature was also implemented there, though in a slightly different way, but roughly went in the same direction. A centralized configuration utility where system administrators could have a view over the complete hardware, assign resources, do some settings and whatnot. The name of the tool is, unsurprisingly, Extended ISA Configuration Utility. It was released in many versions and was branded for all kinds of manufacturers, like Samsung in this case, but as far as I know, the tool itself was not explicitly made for a particular manufacturer. And there were also other branded variants, or even completely unbranded, as in this example. Various versions of the utility had slightly different UI, but essentially the same functionality. For this example, I'll just continue with this Samsung branded version of the tool, since in my opinion it has a better looking UI, especially when you start it the first time. First of all, let's insert this ATI Mach 32 into the first EISA slot and see what happens. As you see, the graphics adapter ATI Mach 32 EISA has been detected and we get the warning about invalid configuration information for slot 1. As I told in the last video, in addition to the BIOS settings on EISA boards, also expansion card settings will be stored in a separate static RAM chip. And exactly for that, we need the previously mentioned utility. So let's see what we get there. This utility is provided to help you set your computer's configuration. You should use this utility the first time you set up your computer and whenever you add additional boards or options. This is exactly what we want. And here is why I found this version of the utility a bit nicer. This one shows the installed hardware as separate cards in the UI. On this mainboard we have 4 EISA slots, which are nicely visualized in this overview. The mainboard itself is shown as system here, and it is marked as OPTI 691-696 for 407 configuration file. What it means I will explain in a minute, but important is that this is the actual mainboard and chipset. In the slot 1 the utility has detected our ATI Mark 32 card. And indeed the card is located in the slot 1. On the PCB you can see that every slot has an accordant name, and the utility automatically detected the graphics card. Now if I go into settings by pressing enter, I will see all possible settings for the board. And to be honest, not too many things which can be set here. Some basic timer, a real-time clock and keyboard settings, as well as the amount and type of the installed memory. If I go down, I will find the ATI Mark 32 card settings. Once again, there is not much what can be set here. The card can be disabled, some kind of graphics engine can be set, whatever this is, probably some acceleration for Windows, and IRQ. Nothing fancy so far, but this hardware is also quite simple. Maybe later we can see something more sophisticated. This tool doesn't only take care of configuration, it also can show some documentation. If we go into View, Switch and Jumper settings, we can find the information about jumpers on that particular piece of hardware. This ATI Mark 32 has a set of switches which are described here. Basically, it is about the video ROM address when alternative ROM shall be used. Also, there are some jumpers for the IRQ number selection. Surprisingly, this is not selectable through the configuration utility, but, well, we have what we have. So, when everything is set, the configuration can be validated and saved into the static RAM chip on the board. That SRAM chip gets powered by the external battery along with the real-time clock IC, so EISA and BIOS settings can survive a system shutdown. And after a reboot, the warning about invalid EISA configuration has gone and the system can be used like any normal ISA system of that time. As I said, I didn't only want to try the EISA hardware configuration, but also do some benchmarks with different graphics cards. So let's take a look at another interesting graphics card, EISA Winner 1000. This card is very unusual. It can be used in both ISA and EISA slots. As you see, on one edge there is an ISA connector, on the other an EISA. The VGA port is located on both sides, and the slot bracket has to be placed dependent from the kind of the bus which you would like to use. A very unique exemplar. Aside from the unusual dual bus support, this is a quite normal card of that time. It has an S3 928 VGA chip and 1 MB of VRAM, which can be extended to 2 MB. I even have some memory for it, but I'll do the upgrade another time. As you see, the card can be used in an ISA slot like so, or EISA slot. Let's leave it in the EISA slot and see what the system reports. The EISA Winner 1000 BIOS is reporting nice. And here we see the invalid configuration in slot 1 again. Obviously, before we had that ATI card there, now it is the EISA. Back to the EISA configuration utility. This time the graphics card hasn't been auto-detected, and I don't know why, but that's okay. Let's add it manually by going into Edit and Add. Here we have a selection of cards, among which we have the EISA as well as the Mark 32 from previous time. Why those cards, you may ask? Well, I'll come back to it in a minute. Now let's select the EISA Winner 1000. Now it asks in which slot it is. And voila, we have EISA Winner 1000 in slot 1, marked as Edit manually. Let's see which settings this card provides. We can select between color and monochrome display modes and set IRQ. DMA resource allocation is listed as an option, but there is only no as an option. Okay, let's save and reboot. The warning has disappeared. The EISA configuration seems to be okay. Now let's take a brief look at another version of the configuration utility. As you see, this one is unbranded. Could be also slightly newer, but the UI is a bit simpler, though the features are the same. This utility is built up as a menu where you go from top to bottom to configure everything. Here you can get some additional information, add or remove boards, or view various settings of the installed hardware. As you see here, it is basically the same information, same settings and entries just as with the previous tool. Mainboard related settings in the beginning and the graphics card related settings below. In advanced menu you can find all kind of information, like which resources are already in use. Would you assign one IRQ to a particular hardware, then this IRQ wouldn't be available for another parts. This is how such a utility can help to easily set up the resources and avoid conflicts without to open the computer case and mess around with jumpers. In this menu you can also see which hardware is installed in which slot and get the information which you need about the expansion cards installed. Like in this case we have the EISA Winner 1000 in the slot 1. This card is manufactured by the German company EISA GmbH. It is a video adapter board. The length of the card is 203 millimeters and it takes 1 amp of current. Well, all kind of very specific information, but how does the utility know this all? Is this information somehow included in the ROM of the expansion cards? Or does the software know everything about all the different cards in the world? Of course not, but let's take a closer look. Let's start with this ID, ELS8041. This ID is stored somewhere in the ROM of the graphics card, and every card has hopefully a unique ID. I guess back then every manufacturer had to register an ID for every piece of EISA hardware in the consortium, the Gang of 9 if you remember. Well, when the utility starts, it reads all those IDs from the ROMs and tries to initialize the configuration for the hardware which has been found. Now, remember how I had to add manually a configuration for the EISA Winner 1000? There were some other entries for various ATI graphics cards as well. Of course, there were many more graphics cards existing in the world back then, so why did the utility show only that small selection? Simply because those were the only configuration files which I previously copied. The information required for the configuration of the hardware is not included in the ROM and is not stored in the utility itself. It is read from so-called configuration files. Here is a selection of configuration files I added. They all start with the exclamation mark followed by the hardware ID and file extension CFG. Since the Microsoft DOS file names were limited to 8 letters, that probably means that the hardware IDs couldn't be longer than 7 characters, I assume. They usually start with letters followed by numbers. The configuration is included not only for the expansion cards, but also for the mainboard itself. The configuration utility lists the mainboard under ID OPT0200, and this is the related file. If we look at it, it is a textual description of the configuration, documentation and options. On top we see the hardware ID OPT0200 once again, and the name OPT691696 407 configuration file, which we saw in the configuration utility. Here we also have the power specification, EISA slot settings, memory and all that stuff about real-time clock, timers, keyboards and so on. For the ATI Mark 32 graphics card we see a similar file. Here we can see the documentation of the dip switches. So the configuration utility basically scans the directory for the configuration files for the hardware IDs found in the system. Those files represent the actual description of the hardware needed for the UI, configuration and also binary representation of the settings saved in the static RAM. The configuration files were similar like drivers and were provided by the manufacturers of the hardware with the actual drivers on the floppy disk. Many people saw it as a weakness, since once the configuration file got lost, it was quite hard to use the hardware, but I don't see how this differs from normal drivers. We all got used to it, that we need drivers for the hardware we use, and back then, in times almost without the internet, searching for drivers was just as hard or easy as searching for those EISA configuration files. They came hand in hand anyway, so I don't see it as a huge spoiler. Obviously, it was hard to find the drivers, EISA configurations and configuration files for the hardware back in the beginning of 90s. But what's about today? Well, I'm happy to report that Mr. Slug, one of the initial team members who helped to shape the RetroWeb project and collected a lot of information about mainboards and chipsets over the years, also maintains a huge collection of EISA configuration files and utilities. Most probably, if there was something related, Mr. Slug will have it in the collection. Here you can find hundreds of configuration files for mainboards, video cards, network cards, SCSI controllers and so on. Here, for example, we have our Opti mainboard under the EISA ID OPT0200. And here is the EISA Winner 1000. I got all the required configuration files from here. The complete archive can be also downloaded as a tar file. Furthermore, there is also an FTP server where all the files are listed once again. Under EISA and sources, you can find all the EISA tools and configuration files, even some drivers. I will put the links in the description. So, and this is how I got this whole stuff configured. Luckily, this is today not as hard as it used to be 30 years ago. The graphics card EISA configuration was very rudimentary, as you saw. That's why I decided to show also something more sophisticated. I already put back and configured the ATI Mark 32 in the slot 1. Now, in addition to that, I'll put another very impressive card, this absolutely massive buffered SCSI controller. As you see, it has 4 MB of dedicated RAM for hard drive caching. Here is the SCSI connector for the hard drive and a floppy connector below. So this is also a floppy controller. But the most impressive chip here is this dedicated 386SX16 CPU. So yes, this card is a computer on its own with dedicated x86 CPU and RAM. Quite a beast, if you ask me. The card is so long that I can insert it only into the slot 4, since other 3 slots are blocked by the CPU. Many cards would still have sufficient space there, but not this whale. I will not connect any hard or floppy drives now. I just want to show you how massive a configuration of such card can look like compared to a simple video adapter. And on the post screen we see once again that there is an invalid configuration now for slot 4. Down below we also see some SCSI BIOS messages, so at least that one was already loaded, though probably the EISA configuration has to be finished first before the controller will be completely usable. Here I would like to point out this ID 15E1. We will see it in a second. Off camera I already downloaded the required configuration files from the mentioned collection. And to no surprise, the file is called AMI15E1, just like the ID we saw on the post screen. Yeah, this is how it looks, but let's rather see it in the UI. And here we are. Slot 1 contains the Mark 32 graphics card, and in the slot 4 we have the AMI SCSI controller. As you see here, we can enable or disable the floppy port, set various DMA channels, set IRQ and the type, if shall be edge or level triggered, ROM address, the amount of memory to be used for the cache, and many other settings. Of course, some later expensive EISA controllers also had configuration software and didn't require to mess with jumpers, but they all had own software each. You required one tool for a SCSI controller, another one for network card. If you had multiple SCSI controllers in the system, especially made by different manufacturers, you needed a specified tool for every one of those. However, if you had an EISA system, you had one tool to rule them all. Also, you could see which resources are already in use by which hardware, so you could easily avoid conflicts. This huge SCSI card, regardless of all the features, has almost no jumpers, so to configure it, you didn't need to open the case of your server. Imagine you had to configure a cluster of those. Then you could save the configuration and just copy it from one machine to another, maybe even over a network. That was quite an awesome invention for system administrators, hence many were glad to pay an extra buck to switch from EISA to EISA on their servers. Well, and once the EISA configuration has been finished, also the warning about the invalid configuration for the slot 4 disappeared and the system was ready to be used. As I said back in the days, the system was designed to be used in servers and workstations, but today I don't plan to use any SCSI or network adapters here. I was rather curious to try something what was not planned by the manufacturer. Test gaming performance and let the EISA, EISA and VLB video cards to run some benchmarks to see how they would perform against each other. For the tests, I selected following cards: an EISA WDC90C30, which belongs to the faster DOS cards, comparable to ET4000 from the performance point of view and has even better compatibility. Second one is this EISA Winner 1000 EISA/ISA cards, which I already presented. This one should be just as fast in EISA mode as the WDC ISA card. The next one is the ATI Mark 32 EISA card, and last but not least an S3 VLB card, which I would like to compare. Luckily, the mainboard allows to use all three bus types and benchmark the results against each other. As I said in my last video, I had previously no experience with EISA because back as it was used, I didn't have an opportunity to work with servers or workstations. And as I came in touch with such systems, more modern buses were already on the market. So this experience was a journey for me, just as it is probably for many of you. My single expectation was that the EISA would be faster than EISA, but not as fast as VLB. So let's see the results. I started the tests with the EISA WDC cards, which should be the reference today. The tests which I selected were from Phil's benchmark pack: 3D Bench, PC Player Benchmark in VGA at 320 by 200, as well as SVGA in 640 by 480. And last but not least, of course, Doom. Oh, and I also included Landmark because that correlates quite good with overall throughput. The benchmarks were all made on a 486DX33. Unfortunately, these BIOS didn't allow a lot of tweaking. You have to keep in mind that this system was made for stability and didn't allow EISA bus overclocking or something like that. Though I set everything to the most aggressive settings with all the wait states set to 0, then, without changing any BIOS settings, I swapped one graphics card after another and ran the tests. Of course, for the EISA cards, I had to do the configuration, but the BIOS settings were the same for all of the cards. And here are the results. 3D Bench finished with same results on all ISA and EISA cards with 21.9 points. With VLB, the benchmark was massive, 30% faster, and did 28 points. In Landmark, the ISA WDC as well as S3 ELSA in both ISA and EISA modes made 3,885 characters per millisecond. So EISA was not faster again. Quite the opposite was actually the case, since the ATI Mark 32 did even worse on 3034 characters per millisecond. That is quite poor results, which was completely destroyed by the VLB graphics card at 16,661 characters per millisecond. It is about 4 to 5 times faster. Interesting values, because ISA bus runs at around 8 MHz, where VLB runs at the full frontside bus clock at 33 MHz. That is about 4 times the clock. In PC Player benchmark, all cards delivered nearly the same performance at the same resolutions. In VGA, I got values between 5.7 and 6 FPS. In SVGA between 2.1 and 2.4 FPS. Once again, EISA was not faster than ISA and VLB was slightly ahead. In Doom, I got a very similar distribution. Unexpectedly, the ATI Mark 32 was again around 10% slower than the other ISA and EISA cards. VLB was faster by about the same margin. Well, those were not the results which I expected. I knew that VLB will definitely beat the EISA, but I didn't expect ISA to run exactly just as fast as EISA, so I thought maybe with a faster CPU the difference will be more obvious and decided to try a 486DX266. This CPU is called Overdrive, but it is basically a normal 486DX266 with the same frontside bus at 33 MHz and multiplier 2. So theoretically doubled CPU performance. And these are the results. In 3D Bench, once again, all ISA and EISA cards delivered the same performance at 33.5 points. VLB graphics card delivered this time almost 50% more with 50 points. In Landmark, the ISA and EISA results were identical to the results with the 486DX33, but VLB card already started its space program and reached the moon, delivering again 5 to 6 times higher values. In PC Player benchmarks now, there was some difference visible between ISA and EISA. Funny enough, in VGA, ISA WDC was still faster than the EISA S3 cards, but ATI Mark 32 was clearly ahead of the ISA card. VLB was once again a little bit ahead, but not by far. In SVGA, the ATI, EISA and S3 VLB were even on the same level at 3.7 FPS, where the EISA S3 delivered only 3.3 FPS and the ISA WDC 3.5. In Doom, the tables flipped again. Here the ISA WDC with 18 FPS was faster than all of the EISA cards. ATI Mark 32 was even the slowest with only 15 FPS. And as always, Doom benefits a lot from VLB and rocks it with 27.6 FPS. For completeness, I decided to max the system out and try a Pentium Overdrive. This CPU is technically not a 486 anymore, but it runs at the same 33 MHz frontside bus with multiplier 2.5, effectively at 83 MHz. I could theoretically take a 486 CPU with a higher frontside bus clock, something like DX50 or DX280, which runs at 40 MHz frontside bus, but that would only increase the gap between VLB and EISA cards and probably decrease the stability. So I decided to raise the CPU speed without increasing the frontside bus. A Pentium Overdrive is pretty much the best what you can get for this board, considering that it has no 3.3 volt CPU support. A Pentium Overdrive has an integrated voltage regulator. And once again, in 3D Bench, all ISA and EISA cards performed at the same level. VLB was almost twice as fast with 76.4 points. In Landmark, all the ISA and EISA cards not only were on the same level, they also were on the same level as with 33 and 66 MHz CPUs. Clearly, there seemed to be a bottleneck through the buses, which both run at 8 MHz regardless of the type of the CPU. In PC Player VGA benchmark, once again, EISA ATI Mark 32 was faster than the ISA WDC and EISA S3 cards, but slower than the VLB graphics card. Remarkably, Mark 32 was right between the ISA and VLB cards. And in SVGA PC Player benchmark, it was even just as fast as the VLB card. However, to be honest, all those numbers were quite near each other, so we barely can speak of a breakthrough in performance. Except for Doom, where the VLB S3 card was once again with 38 FPS about twice as fast as the ISA and EISA cards. And again, unfortunately, both EISA cards were slower than the ISA WDC cards, which is fast, as I mentioned, but I didn't expect it to win against the EISA ATI Mark 32. Well, what do we learn from this story? To be honest, I was surprised by the results a little bit. I did expect that EISA video cards would be always faster than the ISA, but that wasn't always the case. It was clear that VLB would always win the race, but for these tests I even didn't use the fastest VLB card. That S3 is quite average, but still fast enough to clearly win the race. At least in 3D Bench and Doom it was light years ahead. Let's try to interpret those results. The ISA bus is only 16-bit wide and runs at 8 MHz. The EISA runs at the same 8 MHz, but is 32-bit wide. Just as VLB, which is bound directly to the CPU and runs at frontside bus clock. In our test, that means 33 MHz. So from this, we can conclude that at least in DOS games, the performance doesn't depend on the bus width. Well, maybe this is not quite right. Most probably, those DOS games and benchmarks don't use the full bus width and are limited to 16-bit. At least that would explain why there was so little difference between ISA and EISA. VLB, on the other hand, runs with much higher clock and would still have a higher bandwidth. That's why it won so clearly in the most cases. But we shouldn't forget that in some cases EISA was measurably faster than ISA and, paired with a Pentium overdrive, performed in PC Player benchmark just as fast as the VLB card. Still, this doesn't feel like a clear win over ISA, doesn't it? I think the benchmarks have to be extended to Windows 95 or NT, where hopefully the full bus width could be used. Also, don't forget that EISA bus wasn't developed for gaming. It was made for usage in servers and workstations, where usually many expansion cards were installed, network adapters, hard drive controllers, and so on. In an ISA system, where bus mastering was not a thing, the bus would most probably get slower and slower under a heavy load with so many expansion cards. EISA, on the other hand, should scale much more efficiently in such cases, and the system would be more responsive even under a heavy load. At least this is what I think. So gaming on an EISA system is probably not quite as exciting as it might look at the first glance, and another type of benchmarks would be more interesting. Still, I think this board is interesting even for gaming because it has a VLB slot. With a fast VLB graphics card, it would perform nicely in games, and with EISA controllers and network cards, it would scale much better under heavy I/O compared to ISA. I guess I will have to plan more tests under Windows and, as I said, see which benchmarks could really bring EISA to shine against ISA. If you have some ideas, please share those in the comments. I'm really curious what you think about it. As I said, it is also first time for me that EISA is more than just a theory. Well, and the last question for today is, what happens to EISA later? Both buses, EISA just as IBM's MCA, came to their end with the introduction of PCI, which was a 33 MHz 32-bit bus, comparable from the performance point of view with VLB, but with the most benefits of EISA and MCA. Not only was it fast and stable standard, it also integrated that software-driven configuration which we all know today as plug and play. It was not quite as versatile as the EISA configurations which I showed in this video, but it took over the automatic resources configuration of IRQ and DMA. On Pentium systems later we all saw this table here, which showed the list of detected hardware together with the assigned resources. That resources usually couldn't be set directly, but in the BIOS you could set some hints to force automatic assignments to a specific value. The settings were saved in the flash ROM, which didn't need a battery anymore. The automatic assignment came up with unexpected surprises sometimes. That's why sometimes people called plug and play also plug and pray, in the hope that the right resource will be assigned to the right hardware. Well, at least we didn't have to mess around with jumpers anymore and could reconfigure our hardware without opening the computer case. Well, I hope you enjoyed this trip into the history and the benchmarks of EISA. I found this project quite exciting and will try to plan some time to play with it on Windows. Or maybe even Linux, let's see. Unfortunately, I have to give this particular board back to the owner, but I have another pure EISA boards which I can use for such experiments. And probably it would be also possible to borrow these boards in case I would like to make more tests with VLB versus EISA. If you like this video, please don't forget to leave your feedback below. If not, of course as well, there is always space for improvements. And this is it from me for today. Thank you for watching and goodbye.